Our reality might be a spectacular cosmic mirage. This is the core of the holographic principle, a revolutionary idea in physics that suggests our three-dimensional universe is a projection from a two-dimensional surface. It means the solid world you feel and see could be the ultimate illusion. By the end of this journey, you will understand the profound evidence suggesting the universe is not what it seems. We will explore the strange link between black holes and information and investigate how the very fabric of space and time could be stitched together by quantum entanglement. Are you ready to question everything you think is real? That suggestion from Jacob Bekenstein was a quiet earthquake in the world of physics. He proposed something that seemed to defy common sense. Black holes, the most massive objects imaginable, do not store information in the way you would expect. Think of a library. The number of books you can fit inside depends on the size of the building, its three-dimensional volume. But Bekenstein said a black hole is different. Its information content, a property called entropy, is not tied to the space inside it. Instead, it is tied only to the surface area of its event horizon, the point of no return. This was the first clue that the true nature of reality might be written on a two-dimensional surface, not in the three-dimensional world we experience. Then Stephen Hawking entered the story, adding a terrifying twist. He showed that black holes are not entirely black. They slowly leak radiation and can eventually evaporate, vanishing completely. This created a monumental crisis. If a black hole disappears, what happens to all the information about the stars, gas, and matter that fell in? According to the laws of quantum physics, information can never be truly destroyed. This is the black hole information paradox, a profound conflict between our understanding of gravity and quantum mechanics. From the heat of this paradox, the holographic principle was forged. It offered a breathtakingly elegant solution. Perhaps the information was never truly inside the black hole to begin with. Maybe, just like a hologram on your credit card, the three-dimensional reality of the black hole's interior is a perfect projection from the information painted on its two-dimensional surface. This idea does not apply only to black holes. It suggests that for any region of space, everything that happens within its volume, every star, every planet, every one of us, could be entirely described by information stored on its outer boundary. The solid world we live in might be a magnificent illusion, a cosmic projection from the edges of reality. So what exactly is this information that the universe seems to be so carefully painting on its boundaries? We need to think about information not as words in a book, but as the most fundamental building blocks of reality itself. In physics, information represents the distinct states a system can be in. Imagine you are building the most detailed possible model of a tiny region of space. Every particle's position, its spin, its energy level, each of these properties is a piece of information. The total number of these fundamental yes or no questions you can ask about the system, its most basic bits, defines its total information content. This is where things get truly strange. Common sense tells us that a larger volume of space should be able to hold a proportionally larger amount of information. A bigger hard drive holds more data, right? But the universe does not seem to work that way. The Bekenstein Bound, a profound discovery, states that the maximum amount of information you can pack into any region of space is not determined by its volume. Instead, it is strictly limited by the surface area of that region's boundary. Think of a sphere. You would assume the information capacity grows with the sphere's volume, which is massive compared to its thin outer skin. Yet the physics insists the ultimate limit is set only by the area of that spherical surface. This is like discovering that the true storage capacity of a massive warehouse is not determined by the vast space inside, but only by the square footage of its four walls. The universe appears to be fundamentally two-dimensional at its deepest level of information storage. This forces a radical shift in how we view reality. The solidity of the desk in front of you, the feeling of the ground beneath your feet, all of it might not be made of tiny, solid particles in the way we imagine. Instead, what we perceive as matter and energy could be a complex, dynamic pattern of information, a cosmic projection rendered for us to experience. The three-dimensional world feels vast and deep, but the data that creates it might be painted on a distant, two-dimensional canvas, waiting to be decoded. Our intuitive grasp of three dimensions feels absolute. We move forward and back, left and right, up and down. This is the stage on which our entire existence plays out. Yet mathematics and physics have a long history of revealing hidden simplicity beneath apparent complexity. The holographic principle takes this to its ultimate extreme. It proposes that our rich, three-dimensional reality is not fundamental. It is a projection, an emergent phenomenon, much like the three-dimensional image you see floating above a credit card hologram. On that card, there is only a flat, two-dimensional film. Every detail of that stunning three-dimensional image is entirely encoded in the intricate patterns etched onto that flat surface. In a cosmic sense, our universe could be the image, and the film is a distant, two-dimensional boundary. This boundary might be at the very edge of the observable universe, or it could be a surface surrounding a massive object like a black hole. The laws of physics that we take for granted, gravity, the speed of light, the behavior of particles, would then not be the primary rules of the cosmos. They would be secondary. They would emerge from the incredibly complex quantum interactions playing out on that distant, lower-dimensional screen. This does not mean our world is fake or less real in a philosophical sense. The desk is still solid, the coffee is still hot. It means that our three-dimensional reality is a derivative reality, a consistent and useful illusion generated by a more fundamental, simpler description written in two dimensions. Accepting this projection mechanism is the key to unlocking the principle's truly profound implications for the nature of existence itself. But how could such a radical idea ever be tested or proven? A major breakthrough arrived in 1997, thanks to the work of physicist Juan Maldacena. He formulated a specific, mathematically precise realization of the holographic principle called the anti-de Sitter conformal field theory correspondence, often shortened to AD-SCFT. This is not just a philosophical suggestion. It is a concrete duality, a kind of cosmic dictionary that translates between two completely different descriptions of the same reality. On one side of this correspondence, you have a universe with gravity. This is a hypothetical space known as anti-de Sitter space, which has a specific geometry, like a cosmic saddle shape with a negative curvature. Everything in this universe, from stars colliding to light bending, is described by the laws of gravity. On the other side, living on the boundary of this space, is a quantum field theory. This theory has no gravity at all. It describes particles and forces interacting on a flat, lower-dimensional surface, much like the film of a hologram. The stunning claim of AD-SCFT is that these two theories are exactly equivalent. They are two different languages describing the exact same events. Every single thing that happens in the gravity-filled interior, the bulk, has a perfect, one-to-one translation into the interactions of particles and fields on the boundary. A black hole forming in the interior might be described as a specific state of extreme heat in the quantum field theory on the edge. A planet orbiting a star deep inside could correspond to a complex, vibrating pattern of information on the boundary. While our own universe is not a perfect anti-de Sitter space, this correspondence provides a powerful and rigorous toy model. It demonstrates that the holographic principle is mathematically consistent and physically plausible. It shows us that a universe with gravity can genuinely emerge from a world without it, proving that our deepest intuitions about reality's dimensions might be the ultimate illusion. Black holes serve as the ultimate testing ground for this radical idea. They are cosmic Rosetta stones, allowing us to decipher the holographic code of the universe. Their event horizons are not just points of no return. They are the perfect two-dimensional surfaces, the very screens upon which information about everything that falls in is meticulously painted. This is not a guess, it is a resolution to the paradox that started it all. The Hawking radiation that slowly bleeds from a black hole, once thought to erase information forever, is now understood by many physicists to carry that information away. The information is not lost in the singularity. It is scrambled and encoded on the horizon's surface, then emitted back into the universe particle by particle through this subtle radiation. This solves the information paradox in the most elegant way possible, by confirming that the information was never truly inside the three-dimensional pit. It was always on the two-dimensional wall. Think of the black hole's interior, that vast, dark, three-dimensional volume where gravity is king. The holographic principle tells us that this entire realm, with all its terrifying mystery, is completely described by the quantum states vibrating on its two-dimensional event horizon. The interior is the projected image, the horizon is the film. If this is true for the most extreme gravitational environments in existence, places where space and time are twisted beyond recognition, then a profound question emerges. Could the same principle apply to our entire universe? We exist within a cosmic volume, and it too has a boundary at the farthest edge of what we can see. The evidence from black holes suggests that holography is not a mathematical curiosity. It appears to be a fundamental property of spacetime itself, especially where gravity is strong. These cosmic laboratories are showing us that the illusion of depth might be the universe's most consistent and beautiful trick. Your hand feels solid as it rests on the desk, a testament to the tangible world you inhabit. Yet if the holographic principle holds true, this feeling of solidity is a masterful deception. The atoms that compose your hand, the desk, and the very air between them are not, at their most fundamental level, tiny solid objects. They are excitations in a field, dynamic patterns emerging from a cosmic computation happening on a distant two-dimensional surface. Their defining properties, mass, charge, and spin, are not innate qualities of little balls of matter. They are the consequences, the emergent phenomena, born from the frenetic interactions of quantum bits or qubits encoded on that boundary. Think of a massively complex video game. The characters and objects on your screen seem to have weight and substance. They collide and interact, but you know these properties are not physically inside your computer. They are the output of a program, a set of instructions running on a flat, two-dimensional chip. In this cosmic analogy, our three-dimensional reality is the rendered game, and the quantum code on the boundary is the processor. This perspective utterly dissolves the classical idea of substance. It suggests that what we perceive as unshakably physical is, in fact, a kind of computed output, a consistent illusion generated for our senses. This forces a profound and unsettling conclusion. Our most direct experiences, the feeling of a cool breeze or the hardness of stone, are not raw data from the universe. They are highly processed interpretations of a deeper, far stranger reality, written in a language of information we are only just beginning to understand. This profound shift from substance to information leads us to an even more fundamental ingredient, the cosmic glue that binds this entire illusion together. That glue is quantum entanglement. You may have heard of this strange phenomenon where two particles become linked in such a way that measuring one instantly influences the other, no matter how far apart they are. Einstein famously called it spooky action at a distance. In the holographic universe, this spookiness is not just a curious side effect. It is the fundamental mechanism that stitches the very fabric of spacetime into existence. The connection works through the holographic boundary. Picture the quantum degrees of freedom on that two-dimensional surface as a vast network of tiny, interconnected threads. The more these threads are entangled with one another, the more connected, smooth, and continuous the emergent three-dimensional space appears to be from within. It is as if every handshake between these entangled particles on the boundary weaves another tiny stitch into the tapestry of our reality. This creates the seamless continuum of space we take for granted. But what happens when that entanglement is reduced or severed? The fabric of spacetime itself begins to fray. A profound insight known as the ER equals EPR Conjecture makes this connection explicit. It proposes that a pair of entangled particles, the EPR part of the equation, are actually connected by a microscopic wormhole, or Einstein-Rosen bridge, the ER part. This is not a wormhole you could travel through. It is a geometric bridge in the fabric of spacetime itself, a tiny tunnel of extreme connectivity. When particles are maximally entangled, this bridge is short and stable, creating a smooth, continuous geometry. But if you were to disentangle those particles, the wormhole would stretch and pinch off, effectively creating a tear in the spatial fabric. This means the weird, non-local connections of quantum mechanics are not just a feature of our universe. They are the very source of its spatial structure. Every atom in your body, every star in the sky, exists within a spatial network woven entirely from these invisible threads of quantum connection. The solid ground beneath you is held firm by an unimaginably dense web of entanglement linking every point in space to every other. Without this constant, silent communication happening on the boundary, the three-dimensional world we perceive would simply not cohere. It would dissolve into a disconnected, chaotic mess. So the next time you feel the reassuring solidity of the world, remember you are feeling the result of the universe's most fundamental relationship, a relationship that creates space itself from pure connection. This cosmic web of entanglement and information forces a breathtaking question. Could the entire universe, not just a single black hole, be one vast hologram? Some cosmologists are now taking the principle to its logical extreme, making this monumental leap from celestial laboratories to the cosmos as a whole. Our universe is expanding, a fact we have observed for nearly a century. This expansion is driven by a mysterious force known as dark energy, which is mathematically described by a positive cosmological constant. This is a very different environment from the negatively curved anti-de Sitter space that gave us our first precise holographic model. Yet the ambition is to find a similar holographic description for our own real universe. In this grand vision, the two-dimensional surface encoding our three-dimensional reality is not the event horizon of a black hole. It is the cosmological horizon, the absolute farthest limit of what we can ever see. Due to the universe's accelerating expansion, there is a fundamental boundary to our observable universe, a final shell of distance from which light will never reach us. This distant surface, this ultimate edge, could be the cosmic film. It is upon this boundary that the entire story of our universe, every galaxy, every life form, every moment of history, might be perfectly inscribed. The echoes of this idea might even be visible today. The cosmic microwave background radiation, that ancient afterglow from the Big Bang that fills all of space, is our earliest snapshot of the cosmos. Some theorists suggest that the subtle patterns and fluctuations in this background hum could contain faint imprints, the statistical fingerprints of a holographic code underlying reality. Finding such a signature would be like discovering the pixel structure of the universe itself. This application is still highly speculative and far more difficult to model than the CFT correspondence. Yet it represents the ultimate ambition of the holographic principle, to recast our entire cosmic history, from the first flash of the Big Bang to the universe's final fate, as a single, unified holographic projection. If true, it would mean that everything we are and everything we know is a magnificent and dynamic image projected from the edges of space and time. So if the universe is a projection, where are the pixels? The concept of a holographic universe suggests that spacetime itself might not be perfectly smooth and continuous, but instead possess a fundamental graininess at an unimaginably tiny scale. This is the Planck length, a distance so small that it is to a single atom what an atom is to our entire solar system. At this scale, space might be composed of discrete units, a kind of cosmic pixelation underlying the illusion of seamless reality. Detecting this pixelation directly is impossible with current technology, as the scale is far beyond our most powerful microscopes. Yet physicists are ingenious, and they have devised ways to search for the subtle echoes of this granular structure in the cosmos. One of the most promising arenas for this search is the study of gravitational waves. When massive objects like black holes collide, they send ripples through the fabric of spacetime itself. Observatories like LIGO and Virgo measure these ripples with breathtaking precision. The hypothesis is that as these waves travel across billions of light years, the foamy, pixelated texture of spacetime could introduce a faint, high-frequency noise into the signal. It would be like a perfectly smooth wave traveling across a lake that is, upon ultra-close inspection, revealed to be composed of countless tiny droplets. Finding this specific kind of noise in the data would be a monumental clue, a whisper from the fundamental code of reality. Another method looks to the stars, specifically to the most violent explosions in the universe. Gamma-ray bursts unleash titanic amounts of energy, sending photons of light on a billion-year journey to Earth. If spacetime is grainy, these photons of different energies might not all travel at exactly the same speed. The higher energy photons could experience a minuscule delay, as if they were navigating a subtle cosmic resistance. By comparing the arrival times of these photons from the same distant burst, scientists hope to catch spacetime in the act of revealing its discrete nature. Even the highest energy cosmic rays are scrutinized for similar delays. These searches are like trying to detect a single, misaligned thread in a tapestry the size of a continent. The effects are vanishingly small, buried under countless other cosmic signals, but the pursuit is driven by a profound possibility. A single positive result, one clear signature of spacetime's grain, would not just win a Nobel Prize. It would fundamentally reshape our understanding of existence, providing the first direct experimental evidence that our smooth, continuous universe is a beautiful and convincing approximation, projected from a deeper, pixelated truth. This idea that reality is a cosmic projection forces us to question the very nature of existence. If the solid world is an emergent illusion, then what are we, the conscious beings experiencing it? Our deepest intuitions about a fixed and independent reality begin to crumble. This modern scientific principle finds a startling echo in one of philosophy's oldest thought experiments, Plato's allegory of the cave. In that story, prisoners are chained, facing a wall, seeing only the shadows of objects cast by a fire behind them. They believe these shadows are the full extent of reality, having no conception of the three-dimensional world creating them. Are we the prisoners, mistaking the intricate shadow play of a holographic projection for the ultimate truth? The principle also resonates with a strange interpretation of quantum mechanics, which suggests the universe becomes definite only through interaction and observation. In this view, reality is not a collection of isolated objects but a vast web of relationships. The holographic principle gives this web a physical address, locating it on a distant boundary. This does not mean we are living in a computer simulation run by some advanced beings. That idea simply replaces one physical reality with another. The holographic proposal is far more radical. It suggests that physicality itself, the quality of being substantial, is not fundamental. What is fundamental is information and the relationships between its parts. Your sense of a continuous self, making choices in a persistent world, is not invalidated, but it is reframed. Free will and consciousness may not be properties that emerge from clumps of matter in your brain. They could be complex patterns within the cosmic information field, dynamic features of the projection itself. This challenges naive realism, the comfortable assumption that our senses give us a direct and unfiltered readout of the world as it truly is. Instead, our perception is a useful interface, a rendering of a deeper, more abstract reality written in a language of quantum connections. The desk feels solid not because it is fundamentally solid, but because that is the most consistent way for the cosmic code to represent that particular set of entangled information to your conscious mind. We are not just in the universe, we are of the projection, and our act of observation is part of the process that brings its shimmering reality into focus. The idea that our reality is a projection gains even more weight when we find its mathematical home in one of the most ambitious theories of everything, string theory. This framework suggests that the fundamental constituents of the universe are not point-like particles, but unimaginably small, vibrating loops of energy. These strings vibrate in different patterns to create every particle and force we know, from electrons to photons. It is within this rich theoretical landscape that the holographic principle found its most precise and powerful expression. The CFT Correspondence, that cosmic dictionary linking a gravity-filled universe to a quantum boundary, was not discovered in a vacuum. It was born from the mathematics of string theory, revealing a deep and symbiotic relationship between the two ideas. In this duality, the strings and the complex, multi-dimensional objects called brains that exist within the higher dimensional bulk of space are perfectly mirrored by the particles and fields of the quantum theory living on the lower dimensional boundary. They are two sides of the same coin, two completely equivalent descriptions of a single reality. This has given physicists an incredibly powerful tool. Problems that are nearly impossible to solve in one domain can become surprisingly manageable when translated into the other. For instance, understanding the behavior of a specific type of extremely hot, dense quark gluon plasma, a state of matter that mimics the early universe, is an immense challenge using standard quantum field theory. But through the holographic lens, this problem can be mapped onto the much more tractable physics of a black hole in a higher dimensional space. The intense interactions of the quantum soup become the predictable dynamics of gravity and horizons. This cross-dimensional problem-solving has enriched both fields immeasurably, transforming holography from a speculative idea into a central, working pillar of modern string theory. In return, string theory provides the mathematical machinery that makes the holographic universe not just a compelling metaphor, but a concrete and calculable reality. Together, they are weaving a new picture of a cosmos where dimensions are fluid and the very laws of physics emerge from a deeper, vibrating code. Hawking's greatest puzzles seem to threaten the very foundations of physics. If a black hole evaporates into a featureless cloud of radiation, what happens to all the detailed information about the stars and planets that fell in? Quantum mechanics insists that information is never truly lost, it can only be scrambled. Yet Hawking's calculations suggested it was vanishing forever, erased from existence. This black hole information paradox created a deep crack in our understanding of reality. The holographic principle steps in not to patch this crack, but to reveal it was an illusion all along. The solution is as radical as the problem. The information was never inside the black hole to begin with. Think of a burning book. If you only look at the ashes, it seems the story is lost. But what if the words were never printed on the pages? What if they were a projection from a film reel stored safely outside the fire? This is the holographic resolution. All the information about what fell into the black hole is encoded on its two-dimensional event horizon, the ultimate safety deposit box. As the black hole slowly evaporates through Hawking radiation, it is not destroying information. It is meticulously reading it out. Each particle of radiation carries away a tiny piece of the encoded data, gradually releasing the scrambled story back into the universe. This process preserves unitarity, the quantum rule that information must be conserved. The paradox dissolves because we were looking in the wrong place for the data. We were searching the three-dimensional interior when the real story was always written on the two-dimensional surface. While the precise mechanics of how the horizon encodes and transmits this information remain an active area of research, the holographic framework provides a consistent and elegant picture. It turns a catastrophic failure of physics into one of its greatest triumphs, proving the principle's power not just as a beautiful idea, but as an essential tool for solving the universe's deepest mysteries. This holographic lens does not just reshape black holes, it redefines the beginning of everything. Cosmologists are now applying this radical principle to the Big Bang itself, giving rise to a model known as holographic cosmology. In this breathtaking vision, the moment of creation was not a singularity, a point of infinite density and temperature where our laws of physics break down. Instead, the Big Bang was a cosmic phase transition. It was the moment a vast, hot, and dense sea of quantum information, existing on a two-dimensional surface, suddenly crystallized into the three-dimensional spacetime we now call home. Picture a frozen lake on a winter morning. For a time, the water is a liquid, a fluid realm with its own properties. Then, a shift occurs. Molecules lock into place, and the solid, transparent plane of ice emerges. In this analogy, our entire expanding universe, with its galaxies and stars, is the ice. The mysterious, lower-dimensional quantum state that preceded it was the water. The Big Bang was not an explosion from a point, but the moment reality changed its state, freezing from a fluid information field into the geometric structure of space and time. This perspective offers a profound solution to one of cosmology's oldest puzzles, the horizon problem. Our universe is incredibly uniform. The cosmic microwave background, the ancient light from the infant cosmos, has almost exactly the same temperature in every direction we look. This is deeply strange. In the standard model, there hasn't been enough time since the Big Bang for light or heat to travel from one distant region to another to even out these temperatures. They were never in causal contact. The prevailing solution is a period of ultra-fast inflation, a fraction of a second of explosive expansion that smoothed everything out. But holographic cosmology provides a different, perhaps more elegant, answer. In the pre-Big Bang phase, the universe was not yet spatial. It was a non-local quantum system on a two-dimensional surface, where the very concept of distance had no meaning. Every part of this quantum sea was inherently connected to every other part, instantly. It was uniform because it was fundamentally one unified thing. When it crystallized into our three-dimensional world, that primordial uniformity was baked directly into the fabric of the newborn cosmos. No inflationary spandex is required to stretch it smooth, because it was born perfectly smooth from a state where separation was an illusion. While this model remains highly speculative and is a frontier of theoretical physics, its power is undeniable. It demonstrates how the holographic principle can reframe our most fundamental questions, offering a fresh and potentially revolutionary path to understanding the ultimate origin of our projected reality. This deep thermodynamic link reveals a startling truth about the universe's capacity for disorder. The second law of thermodynamics is one of physics' most unbreakable rules, stating that the entropy of a closed system, its measure of disorder or randomness, can only stay the same or increase over time. You see this everywhere, from ice melting in a warm drink to the relentless fading of a star's light. In our familiar three-dimensional world, you would naturally assume that a larger volume of space could hold a proportionally larger amount of disorder. A bigger room can become much messier than a small closet, but the holographic principle shatters this expectation. The maximum possible entropy any region of space can contain is not governed by the volume inside. It is strictly limited by the surface area of its boundary. This is the Bekenstein Bound in action, a thermodynamic rule written directly onto the geometry of reality. It means the universe's ultimate information storage capacity is shockingly small. Imagine a massive, empty sphere of space a billion light-years across. A naive count would assume it could hold an almost infinite amount of information, a near infinite number of ways to arrange particles within its vast volume. Yet the physics tells us the absolute maximum is set only by the area of that sphere's surface, a number unimaginably smaller than the volume it encloses. It is like being told the entire Library of Congress could only ever hold as many books as you could lay flat on its outside walls. This profound connection unifies the laws of heat and energy with the very shape of spacetime. It suggests that gravity, the force that sculpts galaxies and holds planets in orbit, is not a fundamental force in the way we once believed. Instead, gravity may be an emergent thermodynamic phenomenon. Just as the pressure and temperature of a gas emerge from the collective, statistical jostling of countless molecules, the smooth curve of spacetime and the force we call gravity could arise from the statistical behavior of countless microscopic quantum bits on the distant boundary. The pull you feel toward the Earth is not a fundamental attraction, but a statistical tendency, a thermodynamic force born from the universe's relentless drive toward higher states of entropy and disorder, all encoded on a two-dimensional screen. Such a grand and elegant idea cannot escape the scrutiny of skeptics, and rightly so. The holographic principle, for all its explanatory power, faces profound challenges that keep it from being settled science. Its most rigorous mathematical formulation, the CFT Correspondence, describes a hypothetical universe with a specific geometry, a negative curvature. Our real universe, driven by dark energy and expanding at an accelerating rate, has a positive cosmological constant. It is a de Sitter space, a fundamentally different cosmic environment. Translating the beautiful precision of the Holographic Dictionary to our actual home has proven to be incredibly difficult, a puzzle that has stumped some of the brightest minds in theoretical physics. The equations that work so perfectly for one type of universe become messy and intractable for another. This is not a minor technicality. It is the central obstacle preventing us from declaring that our universe is, without a doubt, a hologram. Other critics raise a more philosophical objection. They argue that the ad-SCFT duality is a mathematical equivalence, a powerful computational tool, not necessarily a statement about what is fundamentally real. In this view, the two descriptions are simply different languages for the same physics, like describing a circle using geometry or using an algebraic equation. One is not more real than the other. Just because we can describe a three-dimensional world using a two-dimensional theory does not mean the three-dimensional world is an illusion. It might simply mean that reality has more than one valid description. This perspective cautions us against leaping from a useful mathematical model to a profound metaphysical conclusion. Perhaps most importantly, for all its theoretical elegance, the principle still lacks the one thing that would cement its place in science: direct and irrefutable experimental proof. The subtle imprints in gravitational waves or the delays in gamma-ray photons remain tantalizing possibilities, not confirmed discoveries. Without this empirical evidence, the holographic principle remains a brilliant, compelling, but ultimately speculative framework on the frontier of human knowledge. It is a magnificent possibility, a guiding star for exploration, but not yet a map of the territory we call home. This leads us to a profound and deeply personal question. Where do we, the observers, fit into this cosmic projection? Quantum mechanics has long wrestled with the role of the observer, suggesting that the act of measurement itself seems to crystallize reality from a haze of possibilities. The holographic principle gives this strange idea a stunning new home. If our world is a projection from a two-dimensional boundary, then who or what is actually running the projector? The answer might be that the projector is not a single, distant object. It is the process of interaction itself. Every time a particle collides with another, a photon strikes your eye, or a scientific instrument takes a measurement, that event is not just observing a pre-existing reality. It is actively participating in the translation, converting the abstract code on the boundary into a concrete, three-dimensional event within the projected world. This does not necessarily require a conscious human mind. A rock tumbling down a hill by interacting with the ground is also performing a measurement, a physical act that decodes a tiny piece of the holographic information into the definite reality of sound, motion, and friction. Your conscious experience of seeing the rock fall is just a particularly rich and complex version of this same fundamental process. This perspective dissolves the hard line we imagine between the world and our information about it. What we call reality is not a fixed external stage. It is a continuous, dynamic interaction, a constant rendering of the cosmic code into the sensory and physical experience we navigate every second. Information is not just a description of reality, it is the primary substance. Matter and energy, the things that feel so solid and powerful, are the temporary, tangible expressions of this deeper informational currency. The universe is not a collection of things but a flowing conversation, and every one of us is both a part of that conversation and its ongoing creation. Perhaps the most compelling way to grasp this cosmic projection is to see the universe as a kind of ultimate quantum computer. The two-dimensional boundary theory, with its intricate network of entangled qubits, acts as the processor. It is the cosmic chip running an unfathomably complex calculation. Our three-dimensional reality, with its galaxies, planets, and conscious life, is the breathtaking output of that ongoing computation, rendered in real time for us to experience. This is not a suggestion that some advanced being is running a simulation. Instead, it proposes that the very laws of physics are the algorithms governing this cosmic process. The speed of light, the universe's ultimate speed limit, could be seen as the processing speed of this system, a fundamental constraint on how quickly information can be updated across the cosmic network. The Planck scale, that unimaginably tiny distance, would then be the fundamental pixel size, the smallest possible unit of resolution in the rendered image of space. Think of the most advanced video game you can imagine. The world you explore is vast and visually rich, filled with realistic physics like flowing water and collapsing structures. Yet every single aspect of that world, every leaf on a tree and every ray of light, emerges from the execution of simple binary code on a two-dimensional silicon processor. The game world feels real and three-dimensional, but its true origin is a flat, logical set of instructions. Our universe might operate on a similar, though infinitely more profound, principle. The solidity you feel and the time you experience are the user interface for a cosmic program whose source code is written in the language of quantum information on a distant, two-dimensional screen. This metaphor gives us a powerful framework for understanding how a vast and seemingly complex three-dimensional reality can arise from a set of simpler, lower-dimensional rules, all running on the ultimate hardware of existence itself. This understanding of gravity turns our cosmic perspective inside out. We have long considered gravity a fundamental pillar of the universe, a primal force that sculpts the cosmos from its largest scales down to the trajectory of a falling leaf. Yet the holographic principle presents a radical alternative. Gravity may not be fundamental at all. It could be an emergent phenomenon, a side effect of a deeper, more basic process. Think of the temperature of a gas. If you place your hand above a boiling kettle, you feel a distinct force of heat, but this sensation is not a fundamental force of nature. It emerges from the collective, frenetic jiggling of countless water molecules. Individually, each molecule has no temperature. Only when you consider the statistical average of their motion does the property of heat and the force it exerts appear. Gravity, according to this revolutionary view, is exactly the same. In the two-dimensional quantum theory that lives on the boundary, the description is complete without any mention of gravity. There are only particles and fields interacting according to quantum rules on a flat surface. It is only when this quantum system is translated, or projected, into the three-dimensional bulk of our universe that the familiar force of gravity materializes. The smooth curvature of spacetime described by Einstein's magnificent theory of general relativity is not the primary reality. It is the emergent consequence, the statistical average of the complex, entangled interactions happening on that distant quantum screen. Einstein's equations, which so perfectly predict the orbit of planets and the bending of light, would then be a kind of magnificent approximation. They are the effective, large-scale description of a reality whose fundamental rules are written in a gravity-free quantum language. The force that holds galaxies together and pins our feet to the ground would be a collective illusion, a ghostly effect born from the universe's underlying quantum code. This cosmic projection model reshapes even our grandest speculations about reality's totality. The multiverse, a concept where our universe is just one bubble in an infinite cosmic foam, has long been a staple of theoretical physics and science fiction. Yet it has always faced a formidable challenge. How could we ever test such a thing? Holography offers a breathtakingly concrete interpretation. In this view, each distinct universe in the vast multiverse does not require its own separate, inaccessible dimension of space. Instead, every possible universe corresponds to a different configuration, a unique quantum state of the same fundamental two-dimensional boundary theory. Our universe, with its specific laws of physics and constants, is simply one particular program running on the cosmic computer. Another universe where gravity is stronger or the speed of light is slower is just a different program, a different set of instructions being executed on the same underlying quantum hardware. The process of eternal inflation, a leading multiverse theory where new universe bubbles constantly nucleate from a primordial energy field, finds a new translation. A new bubble universe forming is not a physical expansion into some pre-existing metaspace. It is a phase transition within the quantum field theory on the boundary. It is the cosmic computer switching to a new set of operational parameters, initiating a new rendering of spacetime with slightly different physical laws. Transitioning between these universes, a feat that seems impossible in 3 dimensions, might be understood as rewriting the fundamental code on the 2-dimensional surface. This provides a potential mathematical foundation for the seemingly untestable multiverse, grounding its wild possibilities in the solidity of quantum mechanics and holographic duality. The vast, abstract landscape of all possible universes, a concept from string theory, is no longer a mere metaphor. It becomes the tangible and immense space of all possible quantum states that can exist on the boundary. Every point in this abstract landscape is a unique universe, and our cosmic history is just a single path winding through it. This holographic multiverse is not an infinitely branching tree of realities in a higher dimensional void. It is a magnificent library of potential cosmic codes where our experienced reality is just one volume among an infinite collection, all written on the same 2-dimensional pages. Long before physicists ever wrote an equation, mystics and philosophers were probing the nature of reality and arriving at a startlingly similar conclusion. The ancient Indian tradition of Advaita Vedanta, for instance, speaks of Maya, the captivating illusion of the physical world. In this view, the myriad forms we see, from towering mountains to our own bodies, are not the ultimate truth. They are a grand projection, a cosmic play emanating from a single, unified source of all existence known as Brahman. Our everyday reality, with all its separateness and solidity, is the veil, while Brahman is the only true reality. This is not so different from Plato's prisoners, forever watching shadows and believing them to be all that exists. For centuries, these were profound but purely philosophical or spiritual insights, standing apart from the material world described by science. The holographic principle now builds a breathtaking bridge between these ancient intuitions and the hard language of modern physics. It does not prove the existence of Brahman or validate any specific spiritual path. What it does is far more profound. It demonstrates that the human mind, whether through deep introspection or through the rigorous tools of mathematics and experimentation, has repeatedly stumbled upon the same fundamental suspicion. The solid world we perceive might be a magnificent facade. The feeling that the universe is not what it seems is not a flight of fancy, but a recurring insight that now finds its expression in the precise formulas of quantum gravity. This convergence is not a coincidence. It points toward a timeless human quest, a deep-seated drive to look beyond the shimmering surface of appearances and understand the true, and perhaps far stranger, nature of the cosmos we call home. The mathematics behind this cosmic emergence are as beautiful as they are strange. To understand how a 3-dimensional world can spring from a 2-dimensional source, we must look at a powerful concept in physics known as renormalization group flow. Think of this as a mathematical process for examining a system at different levels of magnification. Imagine you are looking at a photograph on a screen. From a distance, you see a smooth, continuous image of a forest, but as you zoom in closer and closer, you begin to see the individual pixels that compose that image. The renormalization group flow is the mathematical tool that describes how the rules governing the system change as you move between these different scales of observation. In the holographic universe, this concept becomes the very engine that generates an extra dimension. Within the precise framework of the CFT correspondence, the energy scale of the quantum field theory on the two-dimensional boundary is directly mapped to the radial direction, the dimension of depth in the three-dimensional bulk. This is the cornerstone of the entire illusion. Low-energy processes on the flat boundary correspond to events occurring deep within the interior of the gravitational space, far from the edge. High-energy processes, by contrast, describe events happening right near the boundary surface. It is as if the intensity of the interactions on the quantum screen directly translates into a sense of distance and depth in the projected world. The boundary theory does not explicitly contain a third dimension, but its scaling properties, the way its physics changes with energy, creates the perfect mathematical scaffold for that dimension to emerge. This intricate mapping shows us that an extra dimension is not something you always need to build in from the start. It can be generated, synthesized from the rich, layered structure of a quantum system. A seemingly simpler, lower-dimensional set of rules can encode a breathtaking complexity, giving rise to the very fabric of space and the feeling of depth we take for granted. The solid ground beneath your feet feels real because the quantum code on the boundary is running a calculation of immense sophistication, and depth is its most stunning output. This illusion of a solid world is so convincing because the cosmic projection operates with flawless consistency. Its resolution is so unimaginably fine that any graininess is completely hidden from our view. The fundamental pixel size of this universal display is the Planck length, a distance so minuscule it defies everyday comprehension. To grasp its scale, if you were to magnify a single atom to the size of our entire observable universe, a Planck length within that atom would still be smaller than a single tree on Earth. Our most powerful particle accelerators can only probe distances a billion times larger than this. Our biological senses are even more limited, utterly incapable of detecting this underlying granularity. We are, in effect, immersed in a simulation with a resolution so high it appears perfectly smooth. The laws of physics as we know them are the stable, emergent rules of this grand projection. They are not the fundamental code, but the reliable user interface that arises from it. Consider the experience of watching a film. The story feels fluid and continuous, pulling you into its reality. Yet you know the movie is actually a rapid succession of still images, 24 distinct frames flashing by every second. Your brain seamlessly connects these frames, creating the illusion of unbroken motion. Our reality operates on a similar principle, but the frame rate is incalculably faster, and the pixels are Planck-sized. The projection is so seamless that causality and locality are perfectly maintained within our three-dimensional experience. A cause always precedes its effect, and objects are influenced only by their immediate surroundings. This is why you can push a cup and see it move, rather than seeing it randomly teleport or respond to events on the other side of the galaxy. These are not arbitrary rules, they are the necessary, stable properties of the holographic rendering process. The universe maintains its convincing illusion because the underlying computation is governed by unbreakable mathematical laws, ensuring that the world we interact with is coherent, predictable, and feels undeniably real. Roger Penrose proposed a profound rule for the cosmos, the cosmic censorship hypothesis. It suggests that nature abhors a naked singularity. The infinite, lawless point at the center of a black hole must always be hidden from our view, forever cloaked behind the event horizon. This is not just a cosmic courtesy. It is a fundamental requirement for physics to make sense everywhere else in the universe. If we could see a singularity, its infinite densities and broken laws would shatter our ability to predict anything at all. The holographic principle gives this censorship a breathtaking new meaning. The event horizon is not merely a curtain hiding the monster. It is the sensor itself, a cosmic screen that actively translates chaotic destruction into orderly information. The violent collapse of a star into the singularity is not the primary event. The true event is the imprint it leaves on the horizon's two-dimensional surface. All the information about the star, its composition, its mass, its history, is encoded there. The chaotic interior, with its problematic singularity, becomes a secondary reality, a projected image derived from the pristine data stored safely on the horizon's screen. The breakdown of physics at the singularity is contained, not because it is hidden, but because from the universe's perspective, it is not the fundamental description. The real physics, the complete story, is written in a stable, quantum language on the two-dimensional boundary. The horizon acts as a protective buffer, ensuring the singularity's insanity never leaks out and corrupts the coherent, predictable cosmos we inhabit. Time flows around us like a river, an undeniable part of our existence, yet it may be the holographic principle's most brilliant illusion. On the two-dimensional boundary, the quantum theory operates with a time that is simple and absolute, a mere parameter in its equations, much like the ticking of a master clock. But within our three-dimensional world, time is something else entirely. It is woven into the very fabric of spacetime, a dynamic dimension that can stretch and warp, as Einstein revealed. This creates a deep puzzle, the problem of time in quantum gravity. How does our universal, flowing sense of time emerge from a timeless or simply timed boundary? The answer might lie in the universe's most fundamental glue, quantum entanglement. Imagine the countless quantum threads on the boundary as a vast, interconnected network. If these threads are all perfectly synchronized and entangled in a single, frozen state, there is no change, no progression, and therefore no emergent time. But when different parts of this network become entangled with each other in complex, evolving patterns, something remarkable happens. The very act of these connections changing, of new entanglements forming and old ones shifting, creates a sequence of events. This progression from one quantum state to the next, this relational change between parts of the system, is what we perceive from the inside as the relentless forward march of time. Your experience of reading this sentence, the feeling of a moment passing, could be the cosmic projection of a specific shift in the entanglement structure on the distant boundary. Solving this problem is not just a theoretical exercise. It is essential for making the holographic universe feel like our universe, a place where history matters and the future is unknown. The flow of time is the stage upon which our lives play out, and its emergence from a seemingly static code is the final, masterful touch of this cosmic mirage. The relentless forward march of time feels like the most undeniable rule of existence. We remember yesterday but can only guess at tomorrow, a one-way street dictated by the arrow of time. This directionality is intimately tied to the second law of thermodynamics, the universal tendency toward disorder or entropy. A shattered glass does not reassemble itself because that would mean a decrease in entropy, a reversal of time's arrow. But where does this fundamental arrow come from? The holographic principle offers a breathtaking answer, written in the language of quantum entanglement on the cosmic boundary. The thermodynamic arrow of time we experience in our three-dimensional world may not be a fundamental law at all. It could be a direct projection of something happening on the two-dimensional screen, the increase of boundary entanglement entropy. As the quantum system on the boundary evolves, its web of interconnected threads becomes exponentially more complex and tangled. New entanglements form, creating a richer, more intricate network. This process of increasing quantum complexity and connection has a direction. It only moves toward greater entanglement. From our perspective within the projected universe, this fundamental progression on the boundary is translated into the irreversible increase of thermodynamic entropy we see all around us. The cooling of a star, the mixing of cream in coffee, the fading of a memory, all these expressions of time's arrow are shadows of a deeper quantum computational process. The reason you cannot unburn a log is not just a rule about ashes and smoke in our world. It is a consequence of the fact that the quantum information describing that log, once transformed by fire, has become part of a more complexly entangled state on the boundary, a state from which it cannot simply return. This provides a profound explanation for why time has a single direction. The flow from past to future is not a primitive feature of the cosmos, but an emergent consequence of how the universe processes information. Our unshakable sense of time, the very stage upon which our lives unfold, appears to be the ultimate holographic effect, a grand and continuous rendering of data from a quantum system that is forever growing more connected. The path ahead for holographic research is as vast and uncharted as the cosmos it seeks to explain. While the principle has profoundly reshaped our theoretical landscape, its greatest tests and applications still lie in the future. A monumental challenge is to achieve for our own universe what Juan Maldacena accomplished for a hypothetical one. Our cosmos, with its accelerating expansion driven by dark energy, is a de Sitter space, a very different beast from the anti-de Sitter space of the original duality. Translating the elegant holographic dictionary to this real-world geometry is like trying to write a perfect translation of a poem into a language with an entirely different structure. The mathematics becomes incredibly difficult, but the potential reward is a complete holographic description of everything we see, from the Big Bang to the distant fate of the universe. In parallel, this radical idea is already proving its worth as a powerful practical tool in the world of condensed matter physics. Scientists are using holographic duality to tackle some of the most baffling materials known, such as strange metals. These substances defy classical explanation, conducting electricity with a resistance that behaves in bizarre, linear ways. By modeling a slab of strange metal as a gravitational universe in one higher dimension, physicists can map its perplexing quantum properties onto the more familiar dynamics of a black hole's event horizon. The intense interactions of electrons in the metal become the predictable fall of matter into a black hole, allowing researchers to calculate properties that were once intractable. This same approach is being applied to the long-standing puzzle of high-temperature superconductivity, offering new avenues to understand how materials can conduct electricity without any loss at surprisingly warm temperatures. These applications are not just abstract exercises, they provide real-world validation for the holographic framework, suggesting it holds a deep truth about how complex quantum systems organize themselves. Further out on the horizon, the dream of directly testing the holographic nature of spacetime persists. While we lack the technology to probe the Planck scale, ingenious experiments are being conceived. Some focus on refining the search for that telltale noise in gravitational wave signals, a faint static that could be the grain of spacetime revealing itself. Others look to future quantum gravity experiments that might manipulate entanglement on a scale large enough to see a minuscule change in the geometry of space itself. Perhaps the most profound frontier is the exploding intersection of holography and quantum information theory. Here, physicists are discovering that the very robustness of spacetime, its smooth and continuous appearance might be governed by the same principles that protect a quantum computer from errors. The cosmic projection seems to use a form of quantum error correction, where information about any single point in our three-dimensional world is not stored in one location on the boundary. Instead, it is spread out and scrambled across many entangled quantum bits. This redundancy is what makes space feel solid and stable, preventing the universe from glitching out when minor disturbances occur. Your ability to move reliably through a room without space-time tearing apart could be a direct consequence of a cosmic error-correcting code running on the boundary. The journey to definitively answer whether we live in a hologram is far from over. Each of these paths promises to reveal a deeper layer of reality, showing us that the universe's greatest magic trick is not just its appearance, but the astonishingly elegant code from which that appearance is rendered. So where does this leave us in weighing the evidence for a holographic reality? The case is built on a convergence of profound theoretical pillars. The mathematical elegance of the CFT Correspondence provides a rigorous, calculable blueprint for how a universe with gravity can emerge from a quantum system without it. It transforms a wild idea into a concrete, mathematical duality. This is powerfully complemented by the principle's crown jewel, its elegant resolution of the black hole information paradox. By showing that information is not lost but encoded and radiated from the event horizon, it solves a decades-old crisis that pitted quantum mechanics against general relativity. Then there is the deep thermodynamic link, the Bekenstein Bound, which firmly states that the maximum information or entropy in any region of space is proportional to its surface area, not its volume. This is not a suggestion, it is a fundamental law of physics that directly points toward a two-dimensional information source. Finally, the emerging understanding that spacetime itself may be woven from quantum entanglement provides the mechanism, the very loom that weaves the holographic illusion into the seamless fabric we experience. Together, these strands form a compelling argument that the holographic principle is not just a clever trick, but a fundamental feature of our cosmos. Yet for all its theoretical beauty, the principle faces a formidable challenge: the absence of direct, irrefutable experimental proof. Our universe is not a perfect anti-de Sitter space, and translating this powerful dictionary to our own accelerating, dark energy-filled cosmos remains a monumental unsolved problem. This lack of a smoking gun keeps the principle in the realm of the supremely well-supported theoretical framework, rather than settled scientific fact. Even with this caveat, it stands today as our most promising path toward a complete theory of quantum gravity. It is the best-supported framework we have for bridging the chasm between the quantum world and the cosmic realm, strongly suggesting that the three-dimensional world we perceive is not just an interesting philosophical notion, but a profound physical truth, an emergent reality projected from a simpler, deeper dimension. We have traveled from the event horizon of a black hole to the very edge of cosmological theory, all guided by one revolutionary idea. Our journey reveals a cosmos where three-dimensional space, with all its stars and planets, may be a spectacular illusion projected from a two-dimensional surface. This holographic principle forces us to question everything we thought was solid and real, suggesting that information itself is the fundamental currency of existence, not matter or energy. While profound mysteries remain unsolved, this perspective has already reshaped modern physics, resolving paradoxes that once seemed insurmountable and creating entirely new fields of inquiry. So the next time you find yourself looking at the night sky, remember you might be witnessing a cosmic hologram, a breathtakingly intricate image painted on the distant boundary of reality. If this journey has stretched your perception of what is real, we would love to hear your thoughts in the comments. For more explorations that challenge the limits of understanding, be sure to subscribe.